So in our previous video, we talked about a situation in which we were attempting to draw inferences about mu, the population mean, in a situation in which the population standard deviation was known. And you recall we set off with a null hypothesis that mu was equal to 20. Then we went out and collected our sample, and we found a sample mean y bar was equal to 22.5. And we determined that the probability of getting, in any one particular sample, a sample mean of 22.5 or more, if the true underlying population mean was 20, was a very small value, only 0.0043, and hence we rejected the null hypothesis that the mean was equal to 20. So what are we going to do in this video? In this video, we're going to look at a situation which, unlike the previous one, sigma is unknown. So this is a far more realistic situation, and to motivate it, I'm going to go over kind of a realistic example. So in the example that we're going to cover in this video, we've got a cow, or a bunch of cows, and we've got a rangeland. And what we're interested in knowing is whether or not, as a consequence of grazing by that cow or cows, the amount of plant cover is reduced. So what we're going to do is we're going to set out a series of paired plots. We're going to have these 9 paired plots. There's 1, there's 2, we got a total of 9. And each one of these, we've got a 1 meter squared area that's known as an exclosure. It's fenced off so the cows can't graze. And then outside of that, we have a control plot to which the cows have access. And so for each one of these 9 paired plots, what we're going to do is calculate the difference in plant cover, the delta in plant cover, and based on those 9 samples, we're going to try to draw a conclusion as to whether or not the cows are having a negative impact on plant cover. So in the previous videos, we assumed that the population standard deviation was known. And remember, this population standard deviation is just the square root of the population variance. So now what we're going to do is we're going to estimate the population variance with the sample variance, the population. Oh, we're going to start all over again. Start all over again. It's no big deal. Start all over again. Start all over again. Okay, it's time to start over again. Calm down. 4, 3, 2, 1. In the previous video, we assumed that we knew what the population standard deviation was, and recall the population standard deviation is just the square root of the population variance. In this video, we're going to estimate the population standard deviation with the sample standard deviation, and the sample standard deviation is just the square root of the sample variance. So let's compare some formulas. So what is population variance? It's the sum of all the yi minus mu all squared over n, whereas s squared is going to be the sum of all the yi minus y bar squared over n minus 1. So what are the differences between these two things, between this and this? Well, let's look at the denominator first. And one thing we'll see is mu here versus y bar here. And that's not a trivial difference. So when we think of this value of mu, that's fixed. That's a constant. In contrast, this y bar is what we get when we do the experiment. But recall that if we were to do the experiment on another day, or if someone else were to do the experiment, they'd likely get a different value of y bar. And recall also that the set of all possible small y bar is equal to big Y bar, which is a random variable. So this difference between mu and y bar is really quite important. And the next difference is the difference between capital N and small n minus 1. So capital N is the number of individuals in the population. So that's the population size. We represent that as a big N, and little n is just the size of samples. So the sample size, number of individuals in the sample. And so since big N and little n are obviously going to be two different numbers, we give them two different labels. But what's this minus 1 business here, as opposed to not having a minus 1 business here? Well, remember what the concept is of variance. Variance is just the mean of the squared deviations. So that's what we decided was going to be our index of variability. So it makes sense if you're trying to get a mean that you'd use n, the number of individuals in the population. But why do we have this minus 1 here? The reason we have the minus 1 here, well, I'm not actually going to be able to show it, is that statisticians have been able to demonstrate that if we're going to use sigma s squared to estimate sigma squared, that having n minus 1 in the denominator is going to give us a better estimator. Now, oftentimes when we see this n minus 1, we'll see it referred to as degrees of freedom. So what's that all about? Well, let's consider we have three numbers. And let's say I told you that the mean of those three numbers was equal to 10. What's the first number? Well, the first number could be anything. I mean, the first number could be minus 7. I could have a mean of 10 and one number equal to minus 7. The second number could be anything. It could, for example, be plus 4. I could have a minus 7 and a plus 4 and still have a value of 10. The third number? No. The third number is not allowed to vary. In order to get an average of 10, the third number has to be equal to 33. And so the whole idea of degrees of freedom being n minus 1 is that if we've got three numbers and a given mean, only n minus 1 equal to 2 is going to be able to vary. So the basic idea is that we don't know the population standard deviation, so we're going to estimate it with the sample standard deviation. But that creates a problem. It creates a problem because earlier on we showed that, okay, we could go out and calculate a z value, and that's meant to be a lowercase z with a bar across it, and we could calculate that as y bar minus mu over sigma divided by root n, and we decided that if you took the set of all possible values of z, the little lowercase z, that would be the uppercase z, and that would be normally distributed with mean 0, standard deviation 1, our standard normal distribution. But we can't just take this value s and shove it in here like that, because this value there is a constant, and this value s, well, if I did the experiment, I get one value. If you did the experiment, you collect different individuals, you'd wind up with a different value. So you can't just plop and substitute s for sigma. That ain't going to work. So how are we going to deal with this? The way we're going to deal with this, the answer was provided by this guy called Gossett. So earlier on, we saw this horrible formula for the probability density function associated with a normal distribution. And you remember what a probability density function is. You know what a function is. It's a meat grinder. So you got this meat grinder, and what goes into the meat grinder is y, and what comes out is the probability density function f at y. It's a normal distribution, so it's got these parameters: the variance, the standard deviation, and the mu. And what I said was, yeah, this is the formula, but in this course, we're not going to deal with this formula in terms of solving problems. We're going to use a table that looks like this. And then when you go on to 582, 585, 586, you're not going to use this table either. You're going to use functions like d norm and p norm. And those are functions that are built into the R language. So here's what Gossett did. What Gossett did was come up with a situation and say, okay, if we're not going to know what this value of the variance is, if we're going to estimate it with some value of s, we can come up with a different function, a different meat grinder. And in this different meat grinder, we're going to calculate a value of t, and what comes out is the probability density function of t, which again, you're certainly not going to use this formula. What you're going to use in this course is a table, and in 582 to 586, you're going to use our functions. So in order to understand how a t-distribution works, one way to think about it is in comparison with a z-distribution. So recall, we go out and we collect some data, and we calculate our particular value of z for our particular experiment, lowercase z, y bar minus mu over sigma divided by root n. And the set of all of these is capital Z, uppercase Z, it's meant to be an arrow, uppercase Z, which is normally distributed with mean 0, standard deviation 1. That's our normal distribution. So to solve problems in which we don't know what sigma is, but we estimate sigma with s, we're going to calculate a different statistic. And that different statistic is going to be the lowercase t statistic, and it's going to be y bar minus mu over s divided by the square root. So you can see we're substituting s for sigma, and the set of all these would be a random variable that we can illustrate as capital T, and the way we illustrate its distribution is t, and it's only got one argument, the number of degrees of freedom, mu. So, a couple of notes about this things. The first is when we looked at the normal, we actually saw it in two different forms. One is the general form, which was normal distribution with mean mu and standard deviation sigma. And the other was the standard normal, with mean 0 and standard deviation 1. And this was the basis for the table that we used to solve problems. When it comes to the t-distribution, the only one we're going to concern ourselves with in this course is going to be t is distributed with a t value and b, or nu, where this is a number of degrees of freedom. So, in terms of comparing the t-distribution with normal distribution, one of the features of the t-distribution is that it's more variable, which is not surprising because the t-distribution has this value of s that's going to vary from one sample to another, whereas the z-distribution is going to have this value of sigma, which is a constant. So let's compare those two distributions. So here we've got comparisons of the t-distribution with the z-distribution. And in the first instance, we've got a z-distribution in A, and we got a t-distribution with 5 degrees of freedom. And we can see here's our z-distribution is pale, and our t-distribution is in solid. And you notice down here that the t-distribution has a thicker tail. And what these numbers are meant to represent is that's the value for z, that's the value for t, and the difference between these lines captures 95% of the observations. So you can see that the t-distribution is more variable than the z-distribution. And here we've got a very similar thing, except now we've got a z-distribution and a t-distribution with 30 degrees of freedom, and they pretty much overlap. It's hard to see the difference between them. And so, whereas with the z-distribution, 95% of the values would lie between plus or minus 1.96, with the t-distribution and 30 degrees of freedom, 95% of the values would lie within plus or minus 2.045, which really isn't much of a difference. Now, something worth noting is that for those of you who've had statistics courses before, you probably confronted with the idea of, okay, why do you use a t-distribution? And sometimes you might hear use a t-distribution because the sample size is small. Well, strictly speaking, that's not correct. Why do you use a t-distribution? You use a t-distribution because you admit that you don't know what sigma is. And so you're going to estimate it with S, and that brings in additional variability, which requires you to use a t-distribution. So why do folks say this? The reason folks say that is because once the degrees of freedom gets large, once you get degrees of freedom around 0, there really isn't much difference between a t-distribution and a z-distribution. But in terms of why it's used because you're using S to estimate sigma. So now let's go back to our example and think about cows and plant cover. So there's our cow, or a bunch of cows. Here are our paired plots. And so we've got 9 of these. So we have n is equal to 9. We calculate y bar, and y bar is the average difference in cover between the grazed and the ungrazed plots, and that is a value of 1.0. And we calculate S based on these 9 different samples, and we get S is equal to 1.2. So let's do some calculations. So we've got n is equal to 9. We've got y bar, which is equal to 1.0. And we've got S, which is equal to 1.2. So we put them into our formula and calculate T, our sample statistic, as y bar minus mu over S divided by the square root of n, which is going to be equal to 1.0 minus 0 over 1.2 divided by the square root of 9. So most of these numbers are going to be obvious. I mean, that's our y bar, that's our S, and that's the square root of n. Where did the 0 come from? The 0 came from the fact that our null hypothesis, the thing that we're interested in testing, is that the idea that the cattle had no effect. On plant cover. So by setting this value of mu equal to 0, that's going to allow us to test the hypothesis that the true difference in plant cover between the grazed and the ungrazed portions was equal to 0. So that's where that came from. So we do all this algebra, and we come up with a t-value which is equal to 2.5 based on 8 degrees of freedom. And so with that in hand, off we go to our t-table. So the t-table is set up quite a bit differently from the z-table we saw earlier. So we've got a bunch of rows here, and the rows are the number of degrees of freedom. So a row is the number of degrees of freedom, so we're going to be at 8 because we got 9 observations. So we're going to be working in this particular row. And what you have in the body of the table, are these values of t here, and what is shown here are different probabilities, different areas in this location. So this table is oriented very much differently from the Z table that we saw before. So we called it our t value observed was 2.5. And what we want to determine is the probability of being in this right-hand part of the curve. So in order to do that, we operate on our row that says 8, and what we look for is a value associated with 2.5. So we look at that, and here we go. We've got a value. If we wanted a value out here, we want to calculate that value out here, and we know our t value is 2.5. What is that area going to be? Well, that area out there is going to be somewhere between 0.025 and 0.01. And so if we actually did the linear interpolation, we would find that if this t value here is 2.5, the corresponding area here would represent a probability of 0.020. Okay, let's go back to the whiteboard. So instead of going back to the whiteboard, let's just move on to the next slide. So let's assume that the underlying population was normally distributed with mean mu and standard deviation sigma. And let's say we went out and we took a sample and calculated the value of y bar and also the value of s. And based on that, we calculated y bar minus mu over s root n, and we might get a net value of little t right there. And you might do that process again. We might get a value there. We might do it again. Again, we calculate a y bar, we calculate an s, we calculate t using this formula, and we get yet another answer. And we do this an infinite number of times. Well, if you do that an infinite number of times, what you get is this probability density function, which corresponds to the random variable t, which has a t distribution with v degrees of freedom, u degrees of freedom. So this curve here represents the random variable t, the set of all possible values of little t that are obtained by drawing random samples and calculating the value of little t using the obtained y bar and s. But we went out and we did our one experiment. And when we went out and did our one experiment and went through all this algebra, the value we got for t was equal to 2.50. So, if in fact our underlying population had a mean of 0, because that's our null hypothesis, and a value of sigma that was ultimately going to be estimated by s, the probability of getting a value of 2.5 which is what we obtained, would be very tiny, which is equal to 0.020, and therefore we reject our null hypothesis. So recall how this null hypothesis statistical testing works. We're going to assume that our underlying population was normally distributed with mean 0. And this was because our null hypothesis was the cattle were having no effect. And some standard deviation sigma that we confessed we didn't know, but we knew that we could estimate with S, although that would force us to use a t-distribution rather than a normal distribution. And then we went through some perfect, absolutely mathematically correct, undeniably true statistical logic. And what we came up with was we got our own value of y bar, which is equal to 1, our own value of S, which is equal to 1.2, and based on that, if this assumption was correct, the probability of getting a y bar of 1 or more was equal to 0.020, which is a very small probability, and therefore we came back up here and rejected our null hypothesis that the cattle weren't having an effect and decided that they were. And then the very last point I want to make, and it's a bit subtle, you won't be tested on it, but it is kind of important. I just want to plant the seed in your mind. And that is when it comes to statistics, there's two kind of different paradigms for statistics. And one is Bayesian, and the other is frequentist. And again, you don't have to know this, won't be on the exam. Bayesian and frequentist. And for all of this course, and certainly for 582 and 585, the focus is going to be on frequentist. In 586, Fang Liang will do a little bit on Bayesian. But the notion of frequentist statistics is a bit weird. It's a bit weird in the sense that what we want to do is draw inferences about mu based on the single sample we take of y bar. But in order to do that, we have to consider the random variable y bar, which is a set of all possible values of y bar. So in other words, in order to draw inferences based on our single sample, we have to consider all possible samples that might have arisen using the process that we used to draw a single sample. So we'll stop there.